Hello. In the previous lecture, we studied how to create B tree by inserting different elements into the B tree from the scratch. So today we are going to study how to remove the elements from a given B tree. So in order for doing this process, we need to find the minimum number of keys and minimum number of pointers that can be possible for a particular key based on an order of the key. So here you are given with a tree. The elements are 52, 12, 22, 62, 72, 77, 6, 7, 8, 16, 17, 18, 25, 29, 53, 54, 66, 67, 70, 74, 75, 79, 80 and 81. So and you are given with the order of the tree as 5. So if you given the order, you can easily identify the maximum pointer, maximum key, minimum pointer and minimum key. So here the order is equal to 5, maximum pointer, you know, it is P, it is 5, and maximum key is P minus 1, it is 4, and minimum pointer or minimum number of children should be sealed by 5 by 2, it is 3, and minimum key is equal to 2. So we can start our journey. So firstly we can see how what are the possibilities of deletions and what the process of deletion if our intended node to be deleted is in the leaf nodes. Okay, so there are two possible ways in which we can remove the key. So first the leaf nodes may contain the particular node that we are removing node contain the keys which is greater than the minimum number of keys. So example, here we can see minimum number of keys is 2, and this node contains 67, 60, 66, 67, 70. So here we can see more than minimum keys are present in the node. And second case, currently there is only minimum number of keys like this. Okay, here നമുക്ക് ഇവിടെ നോക്കിയാൽ അറിയാം it involves only two data values. So we can start. Firstly we can remove the value 66. So so the value 66 should be searched from the root 52, 62, and between 62 and 72. So we have to move, can find it is 66. So here we can see the number of data value in the node is equal to 3, and minimum key value is equal to 2. So it can easily be removed without few checking, because the minimum key value is equal to 2. So we can easily remove the 66 from the leaf node. Okay, so even though it is removed from the node, it is not violating the minimum keys. So we are removing the particular data value. Okay, so next we can remove the value 25. So here I need to search for 25, 52, and moves to left, 12 and 22. So 22 move to right, so we can see it is 25. So the number of data values in that node is equal to minimum keys. So that is, if we delete any value from that, it will lose the constraint of 2. So we have some different strategies for doing that. In order for doing that, we have to consider the sibling of that particular node. So there are mainly two types of sibling, left sibling as well as right sibling. So in order for doing such process, if a particular node becomes minimum, comes to less than the minimum, we have to consider and the left as well as the right sibling. So here you can see the particular node 25, 29, we need to remove 25, and if we remove the value 25, the node consists only a single element and it violates the minimum constraint. We know that this minimum key is equal to 2. So in that case we have to actually borrow some values from sibling. So we are not directly borrow something, we have to actually merge the particular node, that is 29, with the left sibling as well as the parent 22. Okay, here you can see how we are doing that. So here we can see there is a left sibling for that node. So we have to write like this: left sibling followed by the parent 22, then followed by the right child. Okay, so here it is 29, and from here we can find this, the middle value is 18. So we have to write, after we removed the 25, we have only 29 in the right child. So we have, in that case, we violated the rule of minimum number of keys. So we have to write like this: we have to write the left sibling, or you can also take the right sibling. Here the 29 have only left sibling, so we have to take the left sibling 16, 17, then the parent 22, and then the remaining 29. So there are 5 values. From the 5 value, you have to identify the minimum value and move that minimum value into that parent value, that is, instead of 22 you have to place 18. So we can see, so we have to move 18 to the parent node. So here we combined everything, so the new values will be 52, then the left sibling 12, and current parent is equal to 18, then left of 12 it is 6, 7, 8, and 18, the left of 18 you have 16 and 17, 16 and 17. So 16 and 17 should be here, there. Next is 22 followed by 29, and you have to write the rest of the tree. So if 52 have a right child, there is no change from the above figure, so you have to write directly. So next we need to remove 74. Okay, so in order for removing the 74, we need to search. So okay, we can complete this tree, then it will be more easier. So we need to, if we remove the 74, so better to complete this. So you have to follow like this. We have to redraw every elements in every steps. So it becomes 53 and 54, and it is 74, 75. Sorry, 67, 70, 74, 75. 79, 80, 81. Okay, and from here we need to remove the value 74. So we can see where it is 74. So some 72 we identify it is 74. So after removing 74, what will we do? So we have to check into the left child as well as the right sibling. Okay, so there are 2 siblings. We know that on removing 74, the node contain only one element, it is 75, so it violates the constraint, the minimum key constraint. It is equal to 2. So we need to either merge it to the left child, or we have to either merge it to right child. But if there are right child as well as the left child, then we have to check which sibling contain maximum number of keys or more number of keys. So here when we check in this case, we know that the left child contain only 67, 70, that is only 2 data value, but the right sibling contain 3 data value. So we can, this is good to merge with the sibling which contain more data value. So here we will choose the right sibling. So write like this: we have 74, 75. When on deleting, we first write the left child, then the parent, and then followed by our right child. So it is 80 and 81, and from this list we know 74 need to be deleted, and then the middle element we can find that it is 79. It has to move to the place of 76. 7 or the parent node. Okay, so we can write like that. So here we are writing 79. So instead of 77 we have to write 79 because we merged the node 75 with its parent and right sibling. Then we found the middle element in it is 79 and moved the 79 to the parent instead of 77 and filled the rest of the tree. Okay, next we need to delete 67. So in order for deleting 67, it is equal to minimum number of keys, and we can see that the left child as well as the right child also has minimum number of keys. It is 22. So we can either take the left child or we can take the right child. Okay, so here I am taken the left sibling. Okay, so the left sibling contains 53, 54 and the parent 62, 67 and 70. So you can also merge it with right sibling. Since both the left sibling and right sibling contain same number of data values, we can choose either left or right. So it is better to choose left. Okay, so we combine the element and we need to remove 67 from the list, and now we can see here only 4 elements in the data value. So when we combined with the left sibling, parent and right sibling and removed our deleting value, we can see that here is only 4 element, and we can see that the maximum key value, its maximum key value is equal to 4. We can store 4 elements in a particular node. So here we not need to divide this element with a middle value. So we can combine this key and make a left pointer from 72 and connect it to that particular node. So that's the way when we combine the node, if it is less than the maximum possible key or equal to maximum possible key, then we not need to split the nodes and move the middle value. We only need to merge with parent, left sibling and right sibling and make it as a single node. So here you can see we combined it with the value left of 72. We combined the value and pointed to the left of 72. Okay, so here you can see our new tree which contain many nodes, and here this a single node contain 53, 54, 62 and 70. So next we can remove 16. So here we can see 16 is placed here, and when we follow the 52, 20 and we reach the 16, and on removing 16 we can see that it will become single node, and in the left contain 3 and right contain 2. So we can merge the left sibling and parent and the remaining 70. Okay, so 6, 7, 8, 12, then 16 and 17, and removing we are removing the value 16 from the list, and here it is 5 elements. The 8 becomes the middle element. 8 has to move to the position of 12. Okay, so now you got an element, so a tree like this. Okay, so next so up to now we deleted the data value from the leaf node. So now onwards we can delete the data value from the internal nodes. In the case of internal node, there are also two possible way. When we delete a particular data value from the internal node, we have to replace that data value with either the in-order predecessor or the in-order successor. In-order predecessor of a particular node means the maximum value in its left subtree, and in-order successor means minimum value in its right subtree. Okay, so now we can delete the element 62 which is in the internal node. So in 72 we have to either follow the in order or the in order successor, in order predecessor or in order successor. So in order successor of in order predecessor of 72 or in order successor can be taken. The in order successor contain the minimum right subtree, and in order predecessor you have to take the maximum element from the subtree. So if I am going for in order predecessor, so the maximum value in the left subtree of 72 is 70. Okay, so we have to move that maximum value in the position of 72. Okay, so here you find that the in order predecessor of 72 is 70, and you can take either in order predecessor or in order successor, but while taking you have to count the number of elements in that list. So suppose the number of elements in order successor is greater than in order predecessor, then you go for in order successor. Either if the number of elements in order predecessor is greater than in order successor, you go for in order predecessor. If both the number of elements in order successor as in order predecessor are same, then you choose either predecessor or successor. Okay, so here we rewrite the 72 with 70. And then the remaining values in that particular node 53, 654, 62, 75 and 77. Here we can see that it is not violating any rule. Minimum key values are there, 53, 54, 62, so there is no problem. We just need to swap the minimum predecessor with 72. So there is no minimum problem constraints present in that deleted node. So 53, 54, 62 contain is following the rules. So now we can delete. Okay, next we can delete the element 18. So for that we need to check the in order predecessor, and it contain only 2 elements, and in order successor it contain only 2 elements. So in this case we can see that both the children of 18 have contain only minimum key values. So if we took either left or right, we won't get a minimum number of nodes. So in this case, if the case is like this, both the children have only minimum key values, then we have to merge that particular node. And because we are deleting the parent 18, so we have to merge that particular nodes. So if this is the case, that is a parent is to be deleted and both the children have only minimum number of nodes, then we have to merge the nodes and connect it with the parent, that is 8 is the current parent, 52, and it contains only 8, and the right of 8 we can connect 12, 17, 22 and 29. Here we can see my maximum number of keys is equal to 4, so we don't need to divide this node. We can easily connect it to the position of parent. We joined the left sibling and right sibling and connected is at the child of 8. But when doing this, we found that here there is only one element 8 in the second level, so it is actually violating the rule. So we need to again modify this thing. So in order for modify, we know that if a child or a particular node contain minimum less than minimum number of key, it have to borrow it from the sibling. So here the sibling is 70, 79, so we have to connect it using parent, that is 8, 52, then 70 and 79. Here also we can see the it contain only 4 elements, that is less than or equal to maximum value. So here also we don't need to find the middle element or any splitting is required. Here just write the merged list, that is 70, 79, 6, 7, then 12, 77, etc. Okay, here is the final list. So you have to think about these steps. If merging two nodes is not making a number of keys greater than the maximum, then we don't need to split that node. But if when we merge the deleting node with the left sibling or right sibling, then we have to count the number of keys. If the number of keys greater than the maximum allowed keys, then you have to find the middle and move that middle into the parent. And suppose if we are deleting the internal node, then we have to consider its siblings. Okay, and then you have to either move to the left predecessor or the internal successor. Internal predecessor means maximum value in the left subtree, and internal successor means minimum value in the right subtree. So you have to swap with that trees. But if the left successor and the right successor and left predecessor contain only minimum number of keys, and suppose we are deleting the corresponding parent, then the rule is we have to combine those nodes and make it as the right subtree of the nearby data element.